Hello and welcome to the Chapter 3 podcast on Section 3.5 Empirical Formulas from Analyses. So one of the applications of moles is actually calculating empirical formulas. So we can look at data and we can calculate the formula of the compound, the empirical one. So remember, empirical formulas are the lowest whole number ratio. Okay, so this little flow chart you see at the top kind of illustrates what we would start with. Sometimes they'll give us the percent by mass of elements. We assume that we have 100 grams of the sample, so we change our percentages into grams. Other times they'll give us the grams directly. Then what we do is we take the grams of each element and then we use molar mass to convert them from grams to moles, and then we can calculate a ratio, and I'll explain how we actually do that, and then after you have the ratio, hopefully you end up with an empirical formula. So that's kind of like the simplified steps of how you would calculate, but there will be a couple examples we show. The first one you see here, methyl benzoate is found to contain a certain amount of carbon, hydrogen, and oxygen. What is the empirical formula? So the first thing we do is we take our grams and we convert them into moles by dividing by the molar mass of that atom. We end up with 3 mole amounts, okay? Then what we do, in order to make our ratio, we always choose the mole amount that's the least. And we divide everything by that least mole value, including the least moles by itself. So you end up with 1 for oxygen, 4 for hydrogen, and you get a number that's close to 4 for carbon. So the ratio of carbon to hydrogen to oxygen is 4 to 4 to 1. So the empirical formula would basically be what the ratio is. Now this is the lowest whole number ratio. It doesn't mean that this is the actual formula itself. So just to go back, remember, convert your grams to moles, make your mole ratio. Now in this particular example, and I forgot to bring this up, everything came out to be a whole number. Now there will be instances where you do not get a whole number. Sometimes you'll get instead of 4 you might get like 4.5 or 4.25 or 4.3 repeating or 4.6 repeating. And what you have to do to those decimals is you have to convert them into into whole numbers by multiplying by a number. So like if we had 4.5, to make this a whole number, if this was 4.5, we'd multiply by 2. But when you multiply by 2, you not only multiply the 4.5 value by 2, but you have to multiply every other number by 2 also to kind of keep the proportion or ratio intact. And that'll become more apparent as we do some more examples in class. With a little bit more information, we can take an empirical formula and we can actually calculate the molecular formula. Remember, molecular formulas are always multiples of the empirical formula. So remember, like for instance, C6H12O6 is the molecular formula, CH2N is the empirical formula, and glucose, the C6H12O6, is a multiple of the empirical. So if we actually know the molar mass or the molecular weight, we can actually, after we solve for the empirical formula like we did before, we can divide the molecular mass that's given by the calculated empirical formula mass, and hopefully if we did the empirical formula correctly, we should get a whole number, because that will always be a whole number multiple, and then we can multiply the numbers by the proper subscripts to expand the empirical formula to the true molecular formula. Here's an example here. So let's say we calculated the empirical formula C3H4O3, and then the molar mass of this is 88 grams. Remember, that would be 3 times the weight of carbon plus 4 times the weight of H plus 3 times the weight of O. So that gives us 88 grams. And let's say the molar mass or molecular weight is actually 176 grams. We can divide the molecular mass by the empirical mass to get the multiple. So the molecular formula is double the mass, or the molecular mass is double the mass of the empirical mass. So that means that we would have to multiply the subscripts in the empirical formula by 2. So the molecular formula is C6H8O6. This is a sample empirical formula calculation, and in this one we're given percentages, and we have to find the empirical and molecular formula. So if we're given percentages, the first thing we do is we change those percentages into grams, assuming we have a 100-gram sample, and we convert our grams of atoms, or grams of our elements, into moles of elements by dividing by the molar mass of each element. So 12, 1.008, and 16. And we get these three numbers, 3.22, 9.6, and 3.23. Then what we do is we divide everything by the value that's the least, which is the 3.22. We get 1, of course, and about 1 for the other one, for oxygen. And for H, it ends up being about 3. So the empirical formula, which is EF, is CH3O. Now, the molar mass of the molecule is 62.1. So now that we have the empirical formula, we can figure out the molar mass of the empirical one. So this is the molecular mass. What we have here is the empirical mass. So 12.01 plus 3 times the mass of H plus 16. So the empirical molar mass is 31.03. So we divide the molecular mass by the empirical mass, which is about 2, which means that the molecular formula is double the mass of the empirical, and so every subscript gets multiplied by 2. So that's the difference between the empirical and molecular formula. Another way to use moles is through a process known as combustion analysis, and this is another technique used to calculate empirical formulas. Normally, when we're doing combustion analysis, we're using hydrocarbons or organic molecules. Okay. Basically, what you're doing is you're literally burning the sample, and then you're collecting the amount of carbon dioxide and water that's created. Remember, if we have a combustion reaction, that means that the carbon in the compound is breaking its bonds and forming new ones with oxygen to make carbon dioxide, and hydrogen is doing it to make water. Okay. Now there's some instances where it's only going to be composed of carbon and hydrogen, but oftentimes there'll be another element that's also present, and determined by subtraction will make sense, because if we know how much carbon and hydrogen we have in the original sample, we can subtract those values to figure out how much of the third element is actually present in the original amount. And this little figure kind of shows how they actually collect these things. They collect through absorbers, and then they're able to weigh the difference in weight before and after the combustion occurs and is collected. So it looks very, I know it looks very daunting, but if you kind of break things up into steps and kind of keep in mind what it is you're trying to accomplish, this isn't too bad. Caproic acid is composed of CH and O. So we know the components, but we don't know the we're looking for the composition. We start off with a 0.225 gram sample, and then this is the amount of carbon dioxide and water we get. So we're looking for the empirical formula and also the molecular formula. So this is like everything kind of compacted into one. What we're going to do here is we're going to figure out how much carbon and how much oxygen and hydrogen we have present. Now if you think about it, this combustion reaction, remember we said every combustion reaction involves oxygen, right? And we'll get to that point in a moment. So all the carbon dioxide, all the carbon has to come from the caproic acid. All of the hydrogen in the water has to also come from the caproic acid. However, there are two sources of oxygen. There is oxygen from the caproic acid, and there's also oxygen from the air. Okay, so that's what we're going to do with subtraction. If we figure out how much carbon and hydrogen there is, we can subtract from the original sample to figure out how much oxygen there is. Okay, so in this first step, let's start with figuring out how many moles of carbon we have. So we have our original sample of carbon dioxide from the given, and we convert it into moles. We divide by the molar mass of carbon dioxide, and then we can use a mole ratio to kind of figure out how many moles of carbon there are. We notice that there's 1 mole of carbon atoms for every 1 mole of the molecule, so that's where this 1-to-1 molar ratio comes from, and this is how we get the moles of carbon. The moles of H, we do something very similar. We start with our water. We convert it into moles of water by dividing by the molar mass. But notice in this formula, instead of 1 like for carbon, there are 2 hydrogen moles, 2 moles of hydrogen atoms for every 1 mole of water. So that's why we multiply by 2 here. Now, what we're also going to do here is we're going to figure out oxygen. So this is why this is in red. So this is the subtraction I was talking about. We have the moles of carbon and hydrogen. If we multiply the moles of carbon and hydrogen by their molar masses and subtract from the original amount, we can get the amount of oxygen that was actually present in the original sample. So notice how this is done in a different fashion than the moles of C and H. And again, remember, it's because there's 2 sources of oxygen as far as this combustion reaction occurs. So once we have the mass of O, then we can do what we did, something similar up here to the second half of this calculation, to figure out moles of O. So we divide by the molar mass of O, and we get this number. So the moles of O happens to be the least out of the moles of C, H, moles of C, moles of H, moles of O. So we're going to divide everything by the moles of O. So we get 1 for O, we get about 6 for H, and about 3 for C. So the empirical formula is C3H6O. So we have the molar mass of the molecule, that's 116. What I'm calculating down here in the second and last line is the empirical molar mass based upon the empirical formula. So 3 times the weight of C plus 6 times the weight of H plus 1 times the weight of O, which gives me 58 grams per mole. And remember, to figure out the multiple, we divide the molecular mass by the empirical mass, and we get a number 2. So that means that the molecule is twice the mass of the empirical, so that means we double all the subscripts. And so this is our molecular formula. And again, we're going to do these in class, and I'll try and explain everything again as we work on some examples together. Until next time.